Hi IBSL2. We are going to talk about second derivative tests today and what that tells you about your function. So I just want to remind you guys, I'm going to take you to a little surfing derivative. And what I would like to show you is to think about that tangent line along a curve. So at any point along the curve, if I drew a tangent line, what would that tangent look like and what would it tell me about the curve? So if you guys notice, as I move the surfer along the curve, look at what that tangent line is showing you. And already so far in this unit, we have been discussing how your first derivative tells you whether your original function is increasing or decreasing. So if we take a look at our first derivative, right, which is the slope of our tangent line, as I move the surfer toward a relative max, right at the relative max, our tangent line is horizontal. So again, thinking that the horizontal line has a slope of 0. As my surfer starts to go down toward a relative minimum, notice what happens here. My slope is negative, and therefore my first derivative value should wind up being negative if I did my test value and did my sign diagram. When I get down to the bottom, at my relative minimum, I again have that horizontal line. So again, my slope of the tangent line would be 0. And then as my surfer increases, we see that slope again positive. The second piece that you guys will notice is about halfway between that relative min and the relative max. Notice how my tangent line goes from going through the line, and 1 second. Okay, right now my tangent line is going through that curve, and then as I move, notice how the tangent line is now on the outside. So if I move about halfway, half the tangent line is below the curve, half is above. And then suddenly once I pass that point, now my tangent line is completely above the curve. Right there is called my point of inflection. That is where this curve changes from being concave up to being concave down. That is the piece, that's the other information about our graph, that we find out by taking our second derivative. So the second derivative. We are going to go ahead and try that. So I'm going to come back to my notes for a minute. And let's just take a look at a random curve. So this is some function f of x. Describe the concavity of the following sketch, and does the function curve upwards, downwards, and when does it change? So again, we're not looking at where it's necessarily increasing, decreasing, because that was our first derivative. So now we're looking at, is the curve actually concave down? So is it curved downwards or is it curved upwards? Does it open up or open down? If you think about your parabolas from Algebra 2, right? Where does it open? So at the very beginning here, I'm increasing, however, this curve is opening downwards. And it is opening downwards all the way until probably about this point right here. Then we notice that there's a change, and this curve is opening upwards until about this point right here. Then our curve is opening downwards, and then there's another switch right here, and then the curve winds up curving upward. And I'll just use black for this last piece here. So we actually have 1, 2, 3, 4 changes in concavity. So we actually do change our concavity 4 times. For the sake of our diagram, I'm going to label A where the first change is, B where the second change is, and C where the third change is. When we do our second derivative test, which we're going to do algebraically in just a moment, our second derivative set equal to 0 is going to give us where the A, the B, and the C values are actually occurring, so that we know when our concavity is changing in this diagram. So the second part to that before we move on is notice the different types of concavity change. If you notice at A, the concavity is changing right in between the relative max and the relative min. At point B, it's kind of a similar change. It's a change from a relative min to what it looks like might be a relative max. However, then at C, it actually is not a min or a max. That's called a horizontal point of inflection. when we actually do our algebra in just a moment, we'll notice that there is a change and there is a difference with what we're going to find in our first derivative test and our second derivative test in the sign diagram to tell us information so we can figure out what type of point of inflection is it. Is it a horizontal point of inflection, or is it a point of inflection that occurs between a maximum and a minimum where it's halfway in between those two? So let's go ahead and look at a couple different types. So point of inflection is a point on the curve at which a change of the shape occurs, so the concavity changes. Your first example of that is when you change from a relative max to a relative min, which occurs right here. Second example is going from a relative min to a relative max, which occurs again about halfway. And then your third example is when you continue to increase or continue to decrease, and it occurs where we have that slope of 0 right in the middle, but you're still increasing. So we do change concavity from concave down to concave up, or from concave up to concave down. That does still occur. However, we do not change direction. So our first derivative wouldn't help us in that case because we're not changing direction. So sometimes we can't find those points if we just do the first derivative test, which is why we have to also do a second derivative test, or why a second derivative test would help us here. So let's try now an actual example. I've got two for you today. So point of inflection occurs when x equals some value that we're going to call a, and it happens to be when the second derivative is equal to 0. So that is the part that we're going to focus on. Since we've already done the first derivative, we are going to include both so that we can see what all this information tells us about our function. So for us, we're going to go ahead and do our first derivative. I'll do it in blue. First derivative of x to the fourth, we'll get 4x cubed. And we are going to go ahead and set our first derivative equal to 0. Our first derivative equal to 0, remember that tells you when your function is increasing or decreasing. Well, if 4x cubed is equal to 0, my answer for this, of course, would be x equals 0. We are going to go ahead and do second derivative test here. My second derivative of 4x cubed gives me 12x squared. I'm going to set my second derivative equal to 0 as well to see if I can find any points of inflection. And again, I will have x equals 0. The difference here is that my second derivative test will tell me concavity changes. Just as we set up our sign diagram for the first derivative, we are now going to include our second derivative with our sign diagram. So my sign diagram will now have 2 rows, and it will have a first derivative and it will have a second derivative place. Since 0 is my only point that I actually have any changes occurring, I will go ahead and set up from negative infinity to 0, and then I'll also set up from 0 to infinity. I will go ahead and pick a test value. So my test value for negative infinity to 0 could be negative 1. If I substitute negative 1 into my first derivative, well, negative 1 cubed still gives me a negative answer. So then negative 1 times 4 still gives me a negative value, so I do have negative for my first derivative. If I choose positive 1 for my first derivative test, that will give me a positive value. For my second derivative, if I choose a negative value into 12x squared will come out with a positive result. And a positive value substituted into 12x squared will also give me a positive result. What this now is telling me is that my function goes from decreasing to increasing, and it is concave up. Well, if I'm going to decrease and increase, and I have to be concave up, then pretty much I know my picture is going to look something like that. So I am going from, decreasing to increasing. So that's the first part, and concave up. So I have to be curved upwards, and then the second part increasing and also curved upwards. So my x to the fourth function will look something like this when I actually graph it. It tells us a lot of information that might be useful when we go to graphing or when we start to analyze what these graphs actually represent. So, second example, we'll try this one together as well. Let's go ahead and take the first derivative. And first derivative would give us 4x cubed minus 12x squared. If I set this one equal to 0, I can factor out the 4x squared. And I am left with x minus 3. If I set each of those factors equal to 0, I wind up getting a change in my direction, because this is my first derivative, set equal to 0, so a change in my direction occurs at 0 and at 3. My second derivative test. My second derivative test tells me, well, my derivative is going to be 12x squared minus 24x, and I'm going to set that equal to 0 to check for changes in concavity. So if I set my second derivative equal to 0, I can factor out 12x, and I'm left with x minus 2. And that allows me to have a change in concavity at 0 and at positive 2. Notice how in this example, the values do not match with the first and second derivative. So I have a change in my direction from my first derivative test at 0 and 3, but I have changes in concavity happening at 0 and 2. Because I have different values for the first and second derivative, I'm going to include all of these values when I set up my sign diagram, so I can make sure I'm not missing any details in my graph. So let me extend our page a little bit so we have a little bit more room to work. Let's go ahead and set up our first derivative and our second derivative. And we have a change at 0, so I'm going to include negative infinity to 0. Our next change occurs at 2, so I'll include 0 to 2. Our next change occurs at 3, x equals 3, so we'll include 2 to 3. And then we always want to finish off our domain from negative infinity to positive infinity, so we'll include from 3 to infinity. I can just fit it on my page. All right, so let's go ahead and choose a few test values so I can set up my entire sign diagram. So once you choose your test values, so I chose -1 for negative infinity to 0, and I got first derivative negative, second derivative positive. You can choose 1 for the 0 to 2 interval, 2.5, 2.5 for the 2 to 3 interval, and maybe 4 for the 3 to infinity interval. But your sign diagram should come out to negative, negative, positive for the first derivative, and positive, negative, positive, positive for the second derivative. So here is where our analytical thinking is going to come into play. How do we wind up using the information from the sign diagram to make a sketch of what our picture should look like, what our graph should look like? So here we have, if you think about a function that is decreasing, so we are decreasing, but we are concave up. Decreasing, concave up is that piece of the function. Now we are decreasing, but we are concave down. So we switched to that piece there. Next, we are decreasing, but we are concave up. So now we are this piece. There we go. And then we are increasing and concave up. Okay? And if we want to find where these points actually occur so we can graph it, well, we know that this point occurs when x is 0. We know that this change here, changing from concave down to concave up, happened when x was 2. We know that this absolute minimum actually here, changing from concave up to another concave up, happened when x was 3. So if I actually want to find the points on my original function so I can graph, I will take 0, 2, and 3 and substitute them back into my original function, and then I can graph.